how we get the information out from our electrical signals. So we are looking at something called sounding curves. That's kind of where we are from the end of last day. And this is the kind of system that you can see. This is that time domain EM system. Here's our transmitter, and there's the receiver. The signal that goes in this current loop is a signal, a current that's on, then it's turned off, and then it stays off for a while. Then it's turned on in the other direction. The point is, as soon as that current is turned off, now there's a great big change in the magnetic flux, and that's going to induce currents in the ground. Those currents in the ground are going to produce magnetic fields that can be measured at this transmitter, and we can measure them as a function of time in these individual time channels. So what you're looking at here, the reds just indicate what times you're going to be measuring the data, and that can go from microseconds to milliseconds. Each datum gets plotted, and so this is 10 to the minus 2 milliseconds, and all at higher times here. And you can see that there's a decrease in the amplitude of the signal as a function of time. And this is actually telling you something about the conductivity of your signal. So that's a time domain sounding curve. In the frequency domain, you have almost the same thing. We've got a transmitter that's got a harmonic signal. In this case, it's in here. This was a system that had multiple frequency coils. And then for each of these sets of coils, you get a response in phase and quadrature phase. And so for each frequency, you actually get both a real and imaginary component, and then you can plot that as a function. The important point is that these are your data. You go along, you're sitting over someplace, take a sounding, and you go over here, take another sound. Over here, take another sound. That's your data. It's quite clear that in here, you're not going to be able to see anything about conductivity, not directly, but there's information in there. That's what we have to So I first of all want to kind of give you a sense about what the information is. So this is going to be just a homogeneous half space under here. So here's a vertical cross section. We've got air up here. Here's our transmitter coil. It's 20 meters above the surface of the Earth. Surface of the Earth is a dashed line. The bottom region is a half space of 100 ohm meters. And air, of course, is just really resistant, so we put it as. If I look at the sounding curve for that, this is what I get. So I get magnetic fields that change with the frequency, and I got a real imaginary part. What I want to do is now just say, okay, suppose I've got a different layer in here. Maybe it's a resistive layer, or maybe it's a conductive layer. And we're now coming back to this point that prompted a lot of our investigations. Remember, in the DC resistivity experiment, if we had a layer that was resistive, then we ended up with the current. So if this was the A electrode, and here's the B electrode, that we ended up with currents that were there. So this resistive layer kind of blinded us. Now we want to see, in this particular case, how effective this inductive source is going to be with finding this resistive layer. In other words, if I really, perhaps I want to find this guy. Can I find him? He's resistive? Or what's his signature look like when this is resistive or conductive or really conductive? So this background is going to be 100 ohm meters. And now I'm going to change this guy to be maybe 10 or 1,000 or something. I'm just going to change that resistivity. And I'm going to look to see what's the effect of that on the data. So this is the sounding curve for just a That homogeneous half space looks like that. And now if I put a resistive layer in, just look at this top guy here. That is, I can see the dashed lines here. So that is what I get with that resistive layer. And you see there's hardly a change. So this is kind of interesting. We've got this kind of inductive source, and if there's a resistive layer down there or not, I don't see very much. So this kind of system is going to be very hard to see resistive layers compared to your DC, which was really easy to see. That sometimes looks good. And now look what happens when I make it more conductive. So if I make that thing 10 ohm meters, look at the difference between the solid and the dashed lines. That's huge. So if you are in a situation where you've got, let's say, a conductive layer, at some depth, and that's certainly what we're looking for in some of these water problems, because you could have a clay layer underneath something, and that would be conductive, then that's going to have a very large response. And if you actually made it down to 1 ohm meter, so let's suppose you had saline water in there, kind of getting up that, you see the difference between that response and half space is huge. So the takeaway message here is 2 points. One is that if you've got this kind of inductive source, then you're going to be able to distinguish conductive layers underneath there. If it's a resistive layer, it's not going to work so well. So yeah.
Is there any significance to where that real and imaginary parts intersect on the plots?
Here?
Yeah.
Well, it all kind of, it's going to come about with respect to this sort of fundamental curve here, right? So if you end up getting kind of that induction number equal to 1, okay, then your real and imaginary parts are actually going to be at that same value. So it's a little bit harder to make an equivalent circuit for the Earth, but the physics is still the same, and that's actually what's happening. So here's a couple of guys that you might come across. Here's something called a GEM-3. It's used a fair bit for things like unexploded ordnance work, or just trying to find small metal objects that are fairly close to you. Operates from 60 hertz to 24 kilohertz. You can mount it on a cart. You have a GPS. You could have it strung over your shoulder. You can use it for detecting landmines, all kinds of stuff like that. So these things here are all, the transmitter is sitting in that horizontal thing, and you also have a receiver coil in here. So that's a configuration that you can have. So instead of the transmitter and the receiver being separated, you just have that. There's something called an EM41. So one of the crazy things about electromagnetics, there's always these different numbers, kind of depending upon which company is developing and what version now. I'm choosing this one to show you because A, it's very useful for geotechnical work, and B, it also illustrates some fundamentals. So what we've got here are 2 coils. So you've got 2 coils, and you have 2 people, and each person can be in charge, like Alan could be in charge of the transmitter, and Stefan could be in charge of the receiver, okay? Now, what are your options? Well, first of all, you could be closer or farther apart, right? And generally, there's going to be some kind of correlation there. If you're really close together, then kind of you're seeing a little bit more, in that region between you. As you go farther apart, you kind of extend that depth of investigation. So that's one. So that the separation between the 2 coils, is kind of related to you know, a little bit sort of how far you see. So you're kind of a little bit like that as far as what you're seeing. So if I move these things farther apart, then you're going to be seeing deeper. So now if I move 20 meters apart, you might be seeing that. 40 meters apart, you might be seeing that. Okay, so that's the first thing. The other is that you also want to be always cognizant of skin depth. So we've got this kind of rule of thumb, or this formula, that delta is equal to 500 root rho upon f. And so the lower the frequency, then the deeper your waves can penetrate. So this first one here is at 64 kilohertz, so 64,000 hertz. This next one, we're not going to move the receivers farther apart. We're actually going to lower the frequency to kind of make sure that we get down to those depths. And then here we're going to go down to 400 kilohertz. So those are two things that you have to work with. You can change your separation, and you can change what your frequency is. Good. There's one other thing that you could change. Anybody? Yeah?
I mean, it wouldn't make sense, but you could change the elevation between the two of them. One could be like way high, that'd be stupid, but you could change it.
Well, no. You could. It's not necessarily, it's not stupid, actually. You'll be surprised to know. I'm going to show you for an EF31 that you actually can make use of that. There's one more thing that is particularly important. I don't know, Kyle? Anybody? What else might you change? Al?
The strengths of the fields from the coils?
Good, you could crank up the current in the coil, and that would help. One more fundamental thing, Liam? Pardon me? Well, you got the coils, but yeah.
The size of the coils.
Yeah, size of the coils is good because remember it's the power, the moment, right? The moment is equal to, for coils, what is it, Arno?
I don't know, something that could change the frequency.
No, the moment, when you talk about the magnetic moment of a coil, what are you talking about? Anybody? The magnetic moment of the coil. I take a coil with a loop of, with a current going through it. Then I said, I replace that with a magnet. And the relationship with the magnetic moment is? Not sure if that's what you said. Does it get a star for that? No, it's kind of close. Okay. So the moment, that's really important here, right? Actually, because you want to get a big moment, you want to get a big mother magnet going here, right? So you get a big moment, you can make that by the area larger or the current larger. There's still one other thing. Anybody? Your name is? Okay. Anybody? You actually saw it. You can see it on here. Rotate the coils, right? So why is that important, right? Because if I have a coil, if this is my coil, then here's my magnetic field coming out like that, right? So that means that Alan is going to get, you're going to get a vertical field at you, right? Watch if I turn this guy. So it's hugely different, right? I'm exciting. Now I've got magnetic fields coming this way. So it's just like an whole new different experiment. It is kind of a different experiment. I'm going to get a very different illumination of the Earth and a very different temporary. So those are the things that you've got going for you. You could change your coil spacing, you change the orientation, and you can change the frequencies. So that's what's going on here. You can imagine now, each time I do this, so suppose I started out here, right, with horizontal coils, and then I flip them, or I could do something else. This would be kind of cool, right? I could take one coil that is horizontal, and I could take a transmitter coil and turn it, right? So instead of having coplanar, I could have one parallel to the ground. I could have the other one, horizontally. Right? So you can see all of these different combinations. Each combination provides like a different source that's going to provide different data, and then you got to unravel that stuff. But the main thing is that you want to somehow sense things differently. So imagine again, you're kind of going back to that concussion experiment that I talked about earlier, right? So if I've got a transmitter here and a receiver here, I'm going to get one line of information. I'm illuminating Alan's head in one direction. But the moment that I turn that transmitter or maybe orient it a bit, I'm exciting his head in a different manner. So it's different surveys give different information. The complexity is unraveling that, but we're not going to go there. So that's what's happening here. And this for hydrogeologic purposes is actually used quite a bit. So if you're going to do hydrogeology in regions that have a couple hundred meters or something like that, you may well end up using the system. Here's the one you're going to be doing in the lab, and I'm going to bring the instrument in. It's called an EM31, and it's got a transmitter here and a receiver here. It works at a fixed frequency, so clearly that's limiting, right? Oh, you got one frequency. I used to talk about sounding curves. You got 1 point. So it works at about 10,000 hertz. There's a 4-meter spacing. And you just sling this guy over the top of you, and then you can walk around, which is what I'll show you happen on the expo site. Or you can drag it, or you can do whatever you want with it. But that's it. It's in a fixed coil system. And it's often called a ground conductivity meter. This is probably the most used EM system for geotechnical work. If you're in a region where you're trying to, let's say, locate buried waste, or you're looking for really near surface, conductive pipes or something like this is actually pretty good. So many years ago, this was like well before your times, there was an exposition in Vancouver called Expo 87. And it was down at the area of False Creek. And in those days, there was none of this. I mean, now you go down to False Creek area, that whole corridor is built up. There's huge numbers of buildings, huge density. But at that time, it was just pavilions. So the world came to Vancouver. That's where Vancouver kind of went onto the map. And people saw these images of Vancouver with the mountains, with the sea, and they're like, oh my God, I gotta go visit there. And that is exactly what happened. So this actually opened up Vancouver. After the exposition, there was quite a discussion about what to do with these lands. So these lands were all industrial waste initially. So this is kind of where, here's BC Place Stadium, General Motors, right? This is an area that we're interested in. So at that time it was totally unbuilt up. But you have to imagine now what Vancouver was like, wind that clock back about 150 years, and none of this stuff was here. You go back 200 years, none of this stuff was here. It was all water. So what they did is, they started filling it in. So logs, sand, gravel, junk. So they filled a lot of this in. And then that's where industrial Vancouver became. That's where some sawmills were. That's where they reclaimed all of their electric engines for transportation. That's where they did coal gasification. That's where they did all kinds of dry cleaning stuff. That was all done in this region in here. And there was all kinds of stuff that was just thrown into the ground. And in those days, had no appreciation for, I get, hydrocarbons or dry cleaning fluids or whatever. Out of sight, out of mind. Just dump it in the ground, it's gone. Of course, that's not what happens. So this area after Expo 86 had to be cleaned up. And we felt that from weaving geophysics, felt like, okay, here's a great opportunity to show what applied geophysics could do, because what they had wanted to do was to see what was there. One of the things that was a real consternation for them is that they went in, I forget which engineering company it was, but they went into this region and they had a backhoe, and they just started to, scoop, just kind of narrow little trenches. And they dug this trench that was, I don't know, maybe 3 feet deep or something like that. And when they dug it, they looked at the size, it was all black. Then they waited a little while, and the black started seeping in. So they started to get a seepage of hydrocarbon fluid of some type in here, up here. Well, you can imagine what that would do. I just brought everything to a halt, and then they just said, like, okay, we got to figure out what this stuff is. Is it, is it toxic? Is it some kind of fluorohydrocarbon, or, what is this stuff? So at that point, you want to know, first of all, where this hydrocarbon was, and secondly, where, is there anything else there? So this was an ideal opportunity for geophysicists to come out and try to do some remote sensing. So we took that challenge. The graduate students and the undergraduate students got hugely excited. I mean, it was pretty amazing. And we got every kind of geophysical equipment that we could possibly get at that time. We went down to the expo site and we collected seismic reflection, seismic refraction, ground penetrating radar, time dominium, frequency dominium, magnetics, and DC resistivity, and IP. Everything that we've been talking about here, and we got stuff. Most of the things that had didn't produce as much information as we wanted. Turned out the region was really, really difficult because there was actually a couple of layers of cement. So there was a cement pad on top, and then there was stuff underneath, and there was more cement, and then underneath it was just a bunch of stuff. But the electromagnetics and the magnetics, the electromagnetics, the magnetics, and the VLF, which we haven't talked about, actually turned out to be really useful. On the GPG site, there's background information about all the stuff that went in here. I don't have time to talk about that. And a bit about the site characterization. Here's the picture I want to talk to you about. So this is a region, it's 100 meters by 100 meters. And it's this EM31 that we've got. And we're going to kind of walk in kind of north-south lines like this. And we're going to measure we're measuring the two numbers that we get out. We get an in phase and we get a contra phase. I'm going to show you in a minute how that imaginary part gets converted into an apparent conductivity, and how the in phase part is just a response. But even from these pictures, there is a lot of information. So this is a picture, effectively, of the imaginary part of that data as you're just walking through. And you can see, like there's, kind of uniform stuff in here. There's things that are coming in like this. There's this guy in here. there's a whole, I could give a whole lecture about this, so this one's so interesting because it coincides with a big magnetic anomaly, which we were trying to understand what it possibly, because it's huge. This anomaly in here, if you took one step, you got about a 2,000 nanotesla change in the magnetic field. Remember down at the beach, you had maybe 20 nanoteslas. Here was a couple thousand. And yeah, it caused a lot of consternation. At one point, we thought there was a buried locomotive there. Story, but it's kind of interesting. Anyway, so there's a map, and there's stuff there. There's stuff happening, right? I mean, at this point, I haven't really talked about how, what things are there. And here's the other response. So EM31, one frequency, two numbers, in phase and quadrature phase. Plot them up, get a picture. You got some geotechnical information here that might be useful. So let's just take a look at that. So here's our EM31. And remember this response curve? So at high induction number, so the in-phase part is really big compared to the quadrature. You're really looking at big conductors. Okay? So this is going to be good if you're operating in this mode for getting the big metal structures. When you're working in the lab and with that three-loop system, you found that if you have a vertical plate or a pipe or something like that, you've got this characteristic signature. Remember, you kind of went through all of that stuff. If you change the orientation or the geometry of that to get a dipping plate or horizontal plate or sphere, you still kind of get sort of that same kind of thing. So that's how the EM31 could potentially be used to find good conductors. And if you come back to here, you see these things that are really blue. So blue is negative. These negative things here. So blue is negative, means really big negative responses. So that's all kind of immediately, you're just looking at these guys here and say, wow, I bet you there's some big metal stuff. So that's what happens. And you also experimented with geometry. So first of all, let's look over at here. So if you've got a boom that's north-south, so it's like this. So let's suppose you've got a pipe here, and you've got your EM31, you're going like this, then that is going like this, and you can see you got positive, negative, positive. So that's that characteristic signature, positive, negative, positive. So you see this on the in-phase part, and like, okay, I've got an interpretation. There's a pipe here or something, and it's running in this direction, and if I wanted to look for that pipe, I just probably go right to the most negative part, and I might just find it. Similarly, this guy up here is telling you something. The difference between this and this is just one of orientation. Here we've got the north-south boom that's going like this, and here you've got the east-west boom, which is going kind of parallel to the pipe. So that was also a question that you kind of contended with, is like, what's the difference if I've got a pipe this way and I'm kind of stepping it over like this with my two coils parallel, or if I shift like this. Well, here's a good picture to ground you. This is data from the expo site. Here's a pipe, and here's what the two orientations look like. For finding the electrical conductivity, we're really interested in what's called the low induction number. So we're interested where the quadrature part here is actually larger than the real part. And under the conditions that the station, or the distance between the transmitter and receiver, if that's S, if that's much less than the skin depth, so skin depth you can find from this formula here, right? So whatever the resistivity is, F is 10,000 hertz. If S is much less than the skin depth, then you could use a formula to calculate the apparent resistivity, and that's obtained from this. So if you just have a half space, and then you look at what the measurement is that you're going to get, then the real part is almost zero. But the imaginary part has this particular formula here. So it depends upon the frequency, sigma, S squared, the distance between the transmitter and receiver. So that's what the response is that you would get if you had a homogeneous circuit. So just the same as we did in DC resistivity, let's just take that thing and manipulate it so that we solve for sigma as being 4 times the imaginary part divided by omega mu S squared. So that gives us now a formula for apparent resistivity. So this is exactly the same as we did in DC. And for a half space, the apparent resistivity is actually equal to the true resistivity, conductivity. Okay? So what happens if the Earth is layered? What happens if it's not a half space? So suppose you have something that looks like this. Maybe I can go back to this slide. So let's just stay with this half space here. Remember I said that if I change my coil configurations, I'm somehow sampling the Earth differently? So if I have a vertical, so if I've got a coil like this, and it's, or maybe this is depth here, okay? So now I have a coil that looks like this, so my magnetic field is coming out. I'm sampling the Earth in one manner. If I turn that coil, I'm now going to be sampling differently. So how can we kind of codify that? We codify that in terms of something called a sensitivity function. So that's what we plotted up here. So look at this curve here, for instance. So if I, or maybe this guy, if I've got a vertical coplanar system, so here I am, here's my transmitter, here's my receiver, and if I'm looking, so clearly that's going to illuminate the Earth in a certain manner. And I want to know, like, just how my Earth, okay, which part of my Earth is really responding to this particular coil configuration. And that's where this quantity comes in for your, basically a sensitivity function. In this particular case, the sensitivity for the horizontal coplanar system kind of comes like this. So I've got a horizontal coplanar system, that means I've got a vertical magnetic dipole. My sensitivity function is actually 0 right at the surface. So if I've got horizontal coils, I'm trying to look down, I can't see things. I can see things a little bit deeper, but not right here. And so my sensitivity is more like this. This axis is scale, so that if this is distance s, then by the time I get down here to about 2s, then I more or less have that I can above the surface of the Earth. So the sensitivity function is a function that's kind of telling me how I am seeing into the Earth, and it's plotted at scale with respect to whatever my transmitter receiver distance is. So the sensitivity function for the horizontal coplanar system looks like this. And for the so if I've got coils that look like this, then I tend to see things that look like that. If I have coils that look like, so now they're going into a board, then I see really up close to the surface and not so deep. So just by changing the orientation of coils, I get a different representation, or I get a different amount of information of what I see. So that's those sensitivity functions. Now if I come to this region here where I've got, let's say, a layered Earth, then I still keep the same sensitivity functions, but my apparent conductivity is now sort of a weighted average of what the integral of that sensitivity function is with my true conductivity. So this is sort of the understanding about what this guy actually means, and we're going to explore that more in the lab, where you just have a two player. Now we'll come back to the thing that you had mentioned earlier about lifting things up. An important point is that this sensitivity function is really related to the location of the instrument, right? So as it's sitting right now, okay, I actually might be fairly close, fairly sensitive to Alan, but if I move back this way, this sensitivity function stays with the instrument, and eventually the only thing I'm really sensitive to is the air. There's no conductivity of the air, so that means that the apparent resistivity is going to go right down. So the concept, which might take you a little bit of thought to kind of wrap your mind around, is that the number that I get out is the integral of whatever conductivity I've got with some function. Okay, I'm not sure if you can see that or not. Okay, so you've got some function. So I suppose this is depth, and now we've got some function that looks like that. So suppose this is some depth, so this is Z1, right? And so this is sigma 1, this is sigma 2, right? The number that I get out is going to be the integral of, let's say, this response function with sigma Z, but it's going to be attached to the instrument. So this is actually Z equal to 0. So if I happen to be sitting right on the Earth, now my response function looks like this, and at that point, I'm going to be most sensitive to this conductivity and some of this. So my apparent conductivity is probably going to be someplace between these. If I now take my instrument and pull it back, that means I'm pulling this curve back. It still looks the same. And now I just might be sensitive only to this guy. So, as I said, it might take you just a minute or two to kind of wrap your head around exactly what this means, but the important thing is that this sensitivity function is kind of telling you how you're viewing the big Earth, and it's attached to the instrument. So now if we come back to our expo site, we take those places, well, we could use that apparent resistivity formula, and we get something on that looks, it's a map that looks like this. So this is in ohm meters, and you'll notice that there's a region up here, actually, that's kind of bluish, which is maybe like 40, 50 ohm meters, and it's actually pretty uniform. And that's for the east-west boom. And now if I change my orientation to make it north-south, I get about the same number. So there's actually a whole region in here which is pretty uniform resistivity. And that's the first thing that says, okay, I kind of think that these numbers might be pretty representative of what's really there. In this particular case, we're looking for a hydrocarbon, and it turns out that the hydrocarbon is pretty well characterized by this particular resistivity. So that is actually now a very important piece of information, right? Because now we're able to think, well, maybe this region in here has got some hydrocarbon contaminant, and of course we already know that it did because we dug in one place and had that. So, you know, from the point of view of geotechnical work, well, we've got a region in here that is very likely that's where hydrocarbon. You might be suspicious about stuff like this too, but you know, as a first shot through, this is already telling you quite a bit, because if you initially looked at that 100 meter by 100 meter region, you can't tell. It's just covered up with cement. And then in addition to that, you see that there's these other structures that are coming in through here. So there, you'll still have a quadrature phase component that's associated with pipes and wires, things like that, and that's what you're seeing. So you start to see the information content that you get out by doing actually simple instrument and just drawing up some pictures. These guys here turn out to be metallic objects. There's also something down here. These guys here are wires and pipes, and I'm going to tell you later about this guy. So that kind of takes you through the sort of the understanding of the data. I want to do just a quick couple of case histories. When we first started the course, this was one of the case histories that we were looking at. Remember, as you went through Ireland, you were looking for sand and gravel quarries. So basically you had bog, and then you were trying to find sand and gravel. So bog's got a lot of water in it, and it could be fairly conductive or fairly low resistivity. Sands and gravels, of course, if they're dry, they could be quite resistant. So what was done here, take this region, and you go over, you just go over it with the EM31, and then you convert the quadrature phase data to apparent resistivities, and you end up with a map that looks like this. Not a very high-res map, but you can still see blues, and you can still see red. The blues are the areas of interest. Those are the resistive areas. So immediately, that's telling you, okay, maybe I should concentrate on a couple of these regions in here that are really blue. Okay, so you kind of narrow things down. And now you say, well, I'd like to have a little bit more information than just this EM31. So I'm going to take one of these areas here, and I'm going to design another experiment. Now I'm going to do a DC resistivity experiment. I do a DC resistivity experiment, invert the data, and I get something that looks like this. And again, there's a blue region up here. So this is along one of these trend sections. There's a blue region up here, which is indicating this likely, it's very resistant, so it's very likely sand and gravel. And there was also, because it was interesting enough, worthwhile doing a seismic refraction experiment. And there's some boundaries that are indicated by this blue, this picture. So, put it all together, and in fact, that was sand and gravels. You can see that the geophysics here has actually been really useful. You take an area, you do a reconnaissance with a very simple experiment, just calculate apparent resistivities, find the areas that are perhaps most interesting, follow that up with a more detailed survey, get some more information, and now you could go ahead and start excavating. In more complicated things, we actually want to go ahead and do an inversion. So now I want to take these whole sounding curves and go ahead and do something. So how does this work? So suppose I took, so this is depth, this is resistivity, and I've got a region that has got a very resistive region at top, in this case designed to kind of represent an aquifer, and there's a conductive region, low resistivity. So now I'm going to do an experiment. I'm going to do a frequency domain experiment. So I'm going to take a set of coils, and I'm just going to continue changing the frequency, and I'm going to get the sounding. So here's the real part, and here's the imaginary part. That's it. That's my data. I mean, you can't look at that and make anything out of it, right? But that's your data. I could also do the same with the time domain system, and now I get a single curve, right? Because I'm just measuring the real part. And here's what I get as a function of time. So those are my two data. They don't look alike. They don't frankly mean anything to just by looking at them, just numbers. But they do contain the information about the resistivity. So in order to do that, we've actually got to invert those data. By inverting those data, then what I'm trying to do is to take the data, invert them, and it's the same process we talked about before. In this case, it's 1D, so I'm just dividing it up into a whole bunch of layers. Actually, it was Saudi who did this. They divided a whole bunch of layers, and then solve that problem of trying to find a resistivity structure that fits the data and has got some sense of smoothness. And here's interestingly what you get. With the frequency domain system, you tend to pick out this high resistor in here, and then you really don't see very much. The reason for that is that frequency domain system was really operating at kind of high frequencies. And so it's most sensitive to what's happening at depth. By the time in order to see something down here, you had to go to a frequency that was much lower than the surface. But anyway, this fits the data. So if you did the observe with, or predicted data with this, you'd match those. If you come along to this time domain system, it's measuring later in time, and you're actually able to see this region at depth here. You don't have nearly the resolution that you do up here just because you don't have good enough early time samples. But anyway, that's your representation. So there's quite a few takeaway things here. One is that, frequency and time, they both will tell you something about the Earth. You can't make any interpretation just from the data themselves. You have to invert them. And when you do, one sounding curve doesn't necessarily tell you everything that's there. You need to, make sure that you've somehow got appropriate information by having the right frequencies, the right time channels, and that. But both of these curves actually provide you with some substantial information about what that resistivity structure is. So there's a couple of case histories that we've got. We'll probably come back to them a little bit later, but this at least finishes up all of the material for the EM. So there's no class, of course, on Monday. There's no labs next week. So we have a bit of a breather. So Wednesday we'll have a quiz. And then actually by next Friday, because we only need one class for more material, and that'll be for the IP. So we'll finish up the IP, and then from then on, we'll just review. It is time for you to start thinking about what your individual case history projects would be. Again, just to reiterate, just find something in your field that you connect with, like, okay, that's an interesting problem in geophysics, could play a role. Try to figure out which survey you might want to use. See if there's an app that does something. If there is, that would be great. If there isn't, at least try to scope out, okay, what kind of an app would I want to have to help answer this question? So all we want to do is just kind of tie your problem somehow in with a geophysical technique and bring the haptic. So we're here to answer all kinds of questions about that, but it's time to start thinking about that. And then the individual ones will get combined into a team-based learning, and you decide which one you want to